He picked up the iPad and then it struck 3:30.
Alrighty. What's going on? Let's start off chat a bit about the exam we have. We're going to have an exam on Saturday. So what I'd say, first off, I posted today some extra office hours and stuff going on this week. It's basically the same schedule as for midterm 1. Would highly recommend take advantage of some of those extra hours to go ask questions, whatever. Even just go and study, even if you don't have anything particular to ask, just showing up is a good habit. People there if you have questions, so I really recommend that. As I said, the exam's pretty much identical format to the first one. I think it's pretty similar difficulty. We'll see. I mean, you've just been through a big midterm season, so I know you've been busy with other stuff, so you might not be as prepared at this stage. You got a full week to prepare, right? So take advantage of the time and the extra help and whatnot leading up to that. There's also like the multiple choice practice document is also updated with some more stuff you can take a look at as well. All right, so we're on to an important topic. Today, Wednesday, we have new stuff that's on the midterm. Friday, no new stuff. It's just review on Friday. And in our topics this week are really just the fallout from Faraday's law, right? That was opposed to reality for us. Now we're going to ask, well, why is that law so special in our modern world? We're going to be talking about extremely important topics for engineering, especially those of you wanting to go into electrical engineering, but also some of the others. That is transformers and generators this week. All right, so we built this picture here. We built this nice picture, right? This is our Picasso that has what we call the foundational equations in electromagnetic theory. These four equations here describe every conceivable scenario for electromagnetic fields. This is kind of like the ultimate goal in any branch of physics. Hey, we want a set of equations that always describes everything. Okay, so electromagnetic theory is very special because we have such a set of equations which always describes how the fields will be created and behave and so forth. We also have this law here known as the Lorentz force law to determine motion of charges in fields. Later in the course, you will see that these collective equations are known as Maxwell's equations, the foundational equations of the theory that led to the prediction of electromagnetic waves. Okay, so in the previous class, though, we really focused on just one of these laws. It's called Faraday's law. That's what's up on the board here. Now, while Faraday's law, in general, is this equation we have here in equation 4, what we talked about briefly is that we can compactly express it as equation 5, where the left-hand side we abbreviate as epsilon. That we will call the induced EMF, extremely important today and Wednesday. On the right-hand side, we abbreviate the flux integral as phi b, the magnetic flux. So from a very practical point of view, the statement of Faraday's law is that the induced EMF is equal to the negative change in magnetic flux. Okay, and that practical statement is the basis of modern day transformers and generators and stuff like that. So induced EMF is created by change in magnetic flux. That's going to be the focus of today and Wednesday. So before we get into that, into the stuff that leads us up to transformers, we're going to talk about something called Lenz's law. Now, Lenz's law is a pretty jokes law, honestly. Lenz's law isn't its own equation. It's just this negative sign in Faraday's law. So presumably Faraday had figured out this relationship without the negative sign there. Eventually Lenz came around and said, no, you have the direction wrong. We actually need a negative sign in this relationship, okay? So the negative sign is there. And it has a very important consequence about the way in which fields behave, okay? So Lenz's law, what does it state? It states that the direction of the induced current will flow such that the induced magnetic field opposes the change in flux. Okay, so basically this thing, Lenz's law, when we create an induced current, it's always going to flow in a very specific direction that we're going to talk about here at the start of this lecture. So it's very important. You might have heard people describe this law before as something like nature hates change or something, which I find is a bit rude. I don't know why would we put words in nature's mouth, right? We should just speak about how it actually is, which is that it opposes the change in flux, okay? So basically, we're going to go through this Lenz's law and do a couple figure examples. So basically, what this states is that if we move a magnet towards a current loop, it will induce a current in the loop, and that induced current will make another magnetic field contribution. So you have to ask the question, which way is it going to create that field? It's always going to oppose the change in flux. So it doesn't matter what situation we're talking about here, it has to oppose the change. Similarly, if you move the magnet away, I actually have some diagrams here, it will oppose in the opposite direction. So we'll start with these diagrams. There's actually some better ones on the next slide, but I want to start with the basic idea here. So we have some current loop here. The bottom is towards us, the back is away from us, and we're taking a magnet and moving it towards the loop. This is going to combine a bunch of ideas we've talked about over the last month. When we move this magnet down towards this loop, we are increasing the magnetic flux in the loop. Therefore, according to Faraday's law, we will induce an electric field around the loop, creating a current. Now we have to go back 3 weeks. If we have a current in a loop, it will make a magnetic field through the loop. So not only is our magnet bringing a magnetic field down into the loop, but the loop itself is going to create a magnetic field. So the statement of Lenz's law is a way that we can always figure out what direction will the current flow and what direction will the B point just by using conceptual ideas, not having to use any math. Okay, so let's talk about this. As this magnet comes down here, the B vectors in this loop get bigger and bigger. That changes a flux, causing a current to flow. Which way will the current flow? It will flow such that it makes an induced B that we have with our dashed arrows here in the opposite direction. Why? Because we want to minimize the change. If we're increasing the vectors this way, then we need to create one this way to oppose the change. And in every conceivable scenario, we're trying to oppose the change here with Lenz's law. So we'll get to the next slide in a second. I just want to talk about this other scenario. Let's say now we are pulling the magnet upwards, so we have an upwards velocity here. Now, the fields are downward still, but they're getting weaker as we pull the magnet away. So the current flows in the opposite direction, inducing a magnetic field downwards to again oppose the change. It's all about opposing change. And that's why on Friday when we did our experiment up here, well I guess we were in another class, but when we did the experiment, when you put the magnet in, the current flows one way. When you take the magnet out, the current flows the other way. This is a way of rationalizing why this would be the case. So let's go back to our right-hand rule for the circular loop. The direction of the field, these dashed lines, the field made by the loop, follows a right-hand rule. So if you were making an induced field up, this is on the left diagram, put your thumb in the upwards direction, your fingers will curl around and tell you the direction of the induced current. Same in this situation. If you're inducing a field downwards, your fingers will tell you the direction of the induced current. So just using Lenz's law and the right-hand rule, you can figure out all these directions. There's actually a much better diagram here on this slide that has all of the 4 possible scenarios. On the last slide, we just had north facing down. Now let's consider all the north-south magnet permutations. As we bring this magnet down into the loop, we are increasing the flux downwards, so we induce a field upwards to oppose the change. We can then use a right-hand rule, put your thumb in the direction of the induced beam. It tells us the direction the current will flow. Okay, so we can figure out everything that will happen here just based on Lenz's law and the right-hand rule. Now let's go to the next scenario. Now we have the south end facing downwards. So the south end is here. The arrows go up into the south end of the magnet. So as we pull it away, the field is getting weaker in the upwards direction. We want to oppose that change. So we're going to induce a field that's also in the upwards direction to oppose the rate at which this thing's getting weaker. Again, we use the right-hand rule, and we determine the direction of the current to be around this loop here like this. Okay, now let's do the opposite scenarios. We have a north that is down, but we're pulling away. The north arrows are always down, so it's getting weaker. The arrows are still pointing down, but they're getting weaker as we pull the magnet away. We have to induce a field downwards to oppose the change. So use the right-hand rule, your thumb goes down, your fingers curl around in the direction of current. And finally, we have example D. We're going south end down towards the loop. So the field is getting bigger, but the arrows are pointing up. So we have an increasing magnetic flux with the flux vectors pointing upwards. We have to induce a field downwards to oppose that change. Again, we put our thumb in the direction of the induced B. Our fingers tell us the direction of the current. So these are really the only four scenarios that could happen, and you should be aware of all four and how they work out like that. Now, there is kind of two other scenarios, which is, what if we just stuck a north magnet and sat it there, or flipped it and just sat it there? Well, then there's no change. That would be these two here on the left, right? If the magnet's just sitting there, B is steady, there's no change in flux, there's no induced current, right? Faraday's law only happens if we change the magnetic flux. If the magnet is stationary, the flux is not changing, we don't have that current induced yet.
What would happen if you put the magnet in like sideways?
What would happen if you put the magnet in sideways? Well, it'd be the same situation. It'd be a bit more complicated depending if it's moving or not, but if the magnet's sideways and not moving, there's still no change in flux. If it's sideways and it's moving, presumably the flux will still change some. It'd be a much more complicated situation. We'd have to sit down and work out if it's like perfectly perpendicular or not. But you could do like an angle, maybe work that out a bit easier or something like that. But for our purpose, we're just going to consider it's increasing or decreasing in a linear direction. Okay, so the direction of this induced current is what determines the direction of the induced field. So we're really combining a few ideas here from the course. First, we have a magnet, creates a magnetic field, out of the north end into the south end. Then we take it down into a loop, which increases the flux in that loop, causing a electric field to be created around the loop, according to Faraday's law. That electric field causes a current to flow. Now you have a current flowing in a wire, which creates a new magnetic field contribution. Which way does it go? That's what Lenz's law tells us. Okay, so it's the combination of a lot of ideas here that we kind of package into this conceptual problem of these diagrams. All right, so we're going to get to the kind of main topic of this lecture, which is inductance. Now, basically these induced quantities are very important in modern society, and if you're inducing a current in a straight wire versus a coiled wire, you can get some pretty different phenomena occurring. Now what's important, well first off, these coiled wires, they're utilized in a lot of modern day electronics. We're mainly going to talk about transformers today, But there's stuff like car starters, fluorescent lights, traffic lights. There's a bunch of applications where coiled wires are used in modern electronics. We're going to be introducing, right after the midterm, something called an inductor, which is based on these properties. Anyway, so basically what's going to happen is if we change a current in one coil, so we have one coil sitting up here, and just like we had on Friday, you know that coil we had. Then we had a second, imagine we have a second coil. Remember one of those Faraday experiments? You change the current in the one coil, you all of a sudden get one in the other one, right? This is the basic idea we're going to use for our properties of inductance here, particularly mutual inductance, where we're going to have two coils, we're going to change the current in one of them, that'll make a changing magnetic field in one of them, which will induce a current in the other one, causing current to flow in the other circuit. That's why that one Faraday's experiment worked, actually. So we're going to focus, there's two types of inductance, mutual and self-inductance. We're going to mainly focus for a bit here on what we call mutual inductance. So basically we're going to have a situation where we have two coils, and we're going to talk about how one coil impacts the other coil when you change the current in one. How does that impact the current flow in the other? Right, so if we change the magnetic field in one coil, it'll induce an EMF in the other. This is the basic idea behind mutual inductance. Let's look at a diagram here to talk about what we're talking about.
Move closer.
So, this diagram here is a good one to talk about this phenomenon of mutual inductance. It's the basic idea behind the Faraday's experiment where we had the two coils. So basically, we have a coil here that's looping around a bunch. We'll call it coil 1, and it has N1 number of turns. So this coil's looping around and around, just having a good time here, and it's separate from this second coil. So we have another coil that's a bit smaller. It has N2 number of turns around it. If we are to change a current in this one, and to be clear, see this little I here? We're going to start using little I to be a changing current. So typically earlier in the course, if we had a capital I, we'd say it's the current, like 5 amps or something. We'll use little I to indicate it's a current which is changing, so it's just an alternating current. And basically we will have some function that tells us how this changes as a function of time. It's going to be very important this week and the week after in this course. So basically, we have a current now that is changing. We know before that when we put a current in a coil, we made a magnetic field through the center. Now, if we change that current, like make it go faster, that will change the B field here in the center of the current. Sorry, in the center of the coil. So you can imagine, we're ramping up the current here in coil 1. It's getting bigger and bigger and bigger. That means the B field is getting bigger and bigger and bigger in the middle. What does that mean for our second coil? Well, if we look at our second coil here, the magnetic field from the first coil is now getting bigger and bigger and bigger. What happens when we have an increasing magnetic field through some region? We have to use someone's law. The topic for last Friday. Faraday's law, right? Faraday's law tells us if we have an increasing or decreasing magnetic flux, we will induce an electric field. So by increasing the magnetic flux here in the second coil, we induce an electric field which causes a current to flow, and we have a current flow in the second coil. This is why those Faraday experiments work, where they put the coils side by side, changed one, wow, like magic, there was current in the other. Okay, so this is the basic principle behind that stuff. What we're going to talk about is how can we calculate the EMF in this coil due to the change in current in this coil. Because remember, in the past when we did circuit theory, we needed some battery with an EMF to cause a current. Now we're saying we can induce an EMF through Faraday's law to cause a current to flow. And we can actually calculate that using Faraday's law. It's effectively like what a battery would have done if it was there instead. So let's check that out. So to figure out the EMF, we are going to use Faraday's law. So Faraday's law, in its compact form, equation 10, is what we'll be using here today, a bunch, which is that the induced EMF is equal to the negative change in magnetic flux. And what we're going to ask ourselves for that diagram we just had up, what is the induced EMF in the second coil due to the change in current in the first coil? We want to build that relationship. So, we say that the induced EMF in the second coil is negative time derivative of the flux. Okay, so here we have the flux, which will be the magnetic flux in that coil, times the number of turns of that coil, right? Because it loops around a bunch, and each time there will be an additional contribution to the current. So you have N2, which is a constant. You can pull it out. You're left with that the EMF in the second coil is negative its number of turns times the time derivative of the flux in that coil. Okay? Now, what we want to do is figure out how does this flux depend on the changing current in the previous coil. Right? This is our second coil, coil 2. We want to figure out how does that relate to what we had in coil 1. And how do we do that? We'll get that in a second, but basically, let's just look at the diagram again. We have the current flowing, it's changing. That makes a changing magnetic field over here. So the flux through this one that we have in our equation, and the number of turns in this one that we have in our equation, will tell us what the induced EMF will be here according to Faraday's law. That's fine, but it's actually kind of difficult to figure out what this flux will be in general. What would be much easier, is if we could explain what the induced EMF here is just based on this current I1. And that's the basic rationale behind this mutual inductance stuff we're setting up. We want to figure out the induced EMF in one coil due to the current changing in the other coil, and not even have to talk about magnetic flux at any point. So that's what we're going to do. How do we do this? We do something called, I don't want to use the word cheating, but it's kind of a sneaky move to avoid having to do anything complex. Let's call it that. Basically what we say is we know that the magnetic flux in the one coil is related to the changing current in the other coil. They are proportional. So how do you make any proportionality in an equation? You need a proportionality constant that we'll call C. We will name it some proportionality constant that we don't know. And it ends up not mattering. But it just skips a lot of headache to try and generalize this flux. Okay? So all we will say is that the flux in the one coil depends on the changing current in the other coil, and then we can go ahead and plug that back into our flux expression to have N2 times that constant times the current. And we can replace the flux for the second coil in terms of the current in the first coil, which is our goal. We call this new combination of constants the number of turns times this C we didn't bother defining, mutual inductance. We get rid of the C and we just kind of pretend that never happened. Okay? So basically, mutual inductance, it's the number of turns in the coil times that proportionality constant. It's some property of the coil setup. Okay? So what is it? You have one coil here in my one hand, another coil here in my other hand. Mutual inductance depends on how big is each coil, how far apart are they, what is the angle. It just depends on your setup. So the mutual inductance between two coils is some proportionality constant. We'll get more into this in a little bit here. But basically, mutual inductance is a constant. We call it big M. Okay, now we can go and plug that stuff back in. We can replace the flux stuff we didn't want to have to deal with. N times the flux is equal to M times the current in the previous coil. We can plug that back into Faraday's law here, down here. We see that the EMF in the second coil is equal to negative the mutual inductance constant times the time derivative of the current in the first coil. This is pretty nice. We get an expression here where we can figure out the EMF in the second coil due to the current in the first coil without having to talk about magnetic fields or flux or anything like that at all. So that's essentially what we do here with these mutual inductance equations. This mutual inductance here, we can isolate it in terms of those parameters we had. So we see that the mutual inductance is the number of turns times the flux in that second coil divided by the current in the first coil. Okay, and this is some proportionality constant if we want to find the EMF on coil 2 due to the current in coil 1. Okay, what about the opposite problem? What if we want to find the EMF in coil 1 due to a change in current in coil 2? Well, we're not going to repeat everything. It's just the exact same thing we just did. You get the exact opposite relationship here. So the induced EMF in coil 1 due to the change in current in coil 2 is given by this relationship, where now we have constant M12, which is the turns N1 times the flux 1 divided by the current 2. It's just the exact same thing in reverse. So we have these two EMF equations. Both of them come from Faraday's law. You change the current in one coil, you produce an EMF in the other. You change the current in that coil, you produce an EMF in the other. It goes back and forth like that. But there's a very important fact about these mutual inductance constants. Turns out that M21 and M12 are always the same thing. So the mutual inductance of this one on this one is always the same as this one on this one. It's just M. Mutual inductance, big capital M here. It's the same for both of them. So the number of turns times flux of one divided by the current of the other always ends up being the same in both directions. Okay? So this constant here, M, it's a property shared by the two coils depending on how big they each are, how far apart they are, what the angles are. If you have a custom setup of two coils, there will be a custom M for that particular setup. Okay, so what do we do with this once we have this M value? Well, we plug it back into our Faraday's law equations, and we're left with our final result, which is the induced EMF of each coil due to the current in the other coil. So the EMF in coil 2 is based on the time derivative of the current in coil 1. The EMF in coil 1 is based on the change in current in coil 2. All right, so these relationships we can use in order to calculate the induced EMF in either direction. This is very important in modern day applications. So important that this constant M that we seemingly just pulled out of some shenanigans has its own SI unit of Henry. So the Henry is an important SI unit for mutual inductance, and that M has that unit, which is equal to joules per ampere squared.
Student has a cheat sheet.
So if we have two coils, We can calculate the induced EMF in either direction using these equations here. This is still from Faraday's law, right? We found this from Faraday's law. This just looks a lot easier. No fields, no flux. You just got to know the current. All you need to know is the current. So let's do some examples. So let's say we have some different functions representing the current here. So here we have a change in current in coil 1. What's the induced EMF in coil 2? So this little I we've introduced, we're saying it's a change in current that we can define with some function. So here we have a polynomial function, a cosine function, an exponential function. And to be clear, if I were ever to ask you to do something like this, I would give a chill function like this. I'm not all of a sudden going to pull some anti-chill, like, inverse crazy function to differentiate here, right? Because that's not the point, just the idea that we need to use a differential operation here. So we have some nice reasonable functions here. How would we find the EMF in the other coil? Well, we would just use these equations we just found. So if we want to find the induced EMF in the second coil, we would have to take the derivative of that function defining the current in the first coil, multiply it by m, multiply it by a negative sign. There you have the induced EMF value. So let's go through those examples here. We essentially just need to take a bunch of time derivatives. So we have three functions: the polynomial, the cosine one, the exponential one, and all these details are in the content on OWL, of course, but basically you would just take the time derivative of each of these functions. So you differentiate the t squared, or the cos function, or the exponential function, and you just have your standard results for the derivatives of these functions. But you're not done yet. You have to plug it into the mutual inductance equation here. So epsilon 2 is going to be negative m times the result of that derivative, and you just plug in the result of that derivative, you're left with that induced EMF in the other coil. Okay, so this is how you would calculate the induced EMF in the second coil, which would start powering that second circuit, that induced EMF on the other side. All right. Now we get to the trippier one. That is self-inductance. This one's a bit harder to visualize. If a changing magnetic field induces a current, which induces another magnetic field, a coil can actually do that to itself, and does do that to itself. It's known as self-inductance. So let's talk about this here. If you have a coil, we already know that a current in a coil makes a magnetic field. So if we change the current in that coil, now we have an increasing or decreasing magnetic field in that coil made by that coil. But according to Faraday's law, that changing magnetic field will induce an electric field, which will start inducing a current in that same coil, which will make a magnetic field to oppose that change according to Lenz's law. So this one's a bit trippier. It's a tough one to visualize, but you can imagine, okay, we increase our current, we increase our field inside, therefore we induce a field around, causing another current, which creates another field, and it's just a wild, very dynamic scenario that occurs in these, okay? So the self-inductance L, that's like what M was for mutual inductance. Every inductor or coil has its own inductance.
You increase the current.
Also units Henry. This case is called L. So we're not going to go through all the details. It's the exact same procedure. You get the exact same equation. A coil will induce an EMF in itself, which is negative the self-inductance times the time derivative of its own current. So you can imagine, inductance is a super involved situation. You have a change in current in one coil, it's doing inductance on itself and another coil, which is doing inductance on itself and the original coil, and it's just a wild time, dude. It's just a wild time. So basically inductance, you gotta think about it a bit. It's not something that you can maybe perfectly visualize, but it's a very kind of cool application of Faraday's law. So here's our self-inductance equation. And we're on to transformers. All right, so just to be clear, we have our self-inductance equation here, combined with our mutual inductance equation. We have to use both at once in application. That leads us to the application of transformers. Okay? Now these aren't those fire trucks that transform into robots and start kicking ass and stuff. These are real important devices in modern day power systems. So basically transformers, for some of you might only learn about these in this lecture, but some of you might spend the rest of your life building and working on these things. They're very important in modern day power systems, very cool devices. The basic idea is we want to change the voltage level in one AC circuit to another AC circuit. Remember, the current has to be changing for this to work. Alternating currents are changing. If you are using direct currents, you would have to use something called an inverter to switch it to an AC current to drop the voltage and stuff like that. I believe that's quite common in Quebec to use the direct current inverter approach. I'm not entirely sure, you can look that up. But basically, why would we want to do this? When we want to transmit power over long, let's say from Niagara Falls, where they're making a ton of power, we want it to go a long distance. High voltages are very beneficial for long distance power transmission. But for household purposes, to power the stupid stuff we do, we need much lower voltages. So we need to drop the voltage from the transmission voltage to the one we would use in our houses. That's where these transformers come in. We can use properties of inductance to drop those voltages appropriately. It's very important in power grid construction. You've probably seen something like this before. If you're driving around the city, and maybe you're like, what's that? Well, let's talk about that. These are called electrical substations. If you continue on in double E, you'll probably take a whole course on these things. They're not just transformers, they have other purposes. But basically, they do a bunch, but they also, one of the main purposes is to drop voltages for long distance transit, and then divert it into different neighborhoods and stuff where you can power a crowd. Anyway, so these substations, what we do is we drop the voltage to a more household use. As I said, they're not just for transformer purposes. Now, if you're interested and you're going into double E, you'll take courses. There's a couple of power systems courses. There's a high voltage engineering course where you'll learn a lot of the details about the everyday real transformers that are used in our power systems. In this course, like anything in intro physics, we typically will talk about the idealized, simplified picture to get a basic idea of the fundamentals. But if you take one of these upper year courses in engineering, you'll learn a lot more about the realities of building these things that have real power loss and stuff like that. We're just going to do the ideal ones. So let's talk about ideal transformers. Basically, we're going to use the inductance property we've been talking about in this lecture to talk about what an ideal transformer is and does. We will have two coils and use our mutual and self-inductance equations to describe what happens with the transformer. So with an ideal transformer, we are saying that all of the magnetic flux from one has a perfect linkage to the other, so we'll call them primary and secondary coils. All of the power inputted to the first coil equals all of the power outputted by the second coil. It is 100% efficient. This is not the case in actual power systems when you build power grids and stuff. You will have some energy loss in this process. I'm not exactly sure what that percentage is. It'd be a cool thing to look up later if you're interested. Anyway, let's look at it. What does it look like, these ideal transformers? So, we have some, what we call primary circuit. That's what all the P's are for. It is making some alternating current, maybe Niagara Falls or something. We'll talk about generators on Wednesday. But basically, we have the primary current here. It's creating, or primary circuit, it's creating a primary current that's going into the primary coil. It has a primary terminal voltage here. And it has a number of turns, and P, that is the number of turns of the primary coil. If we want to drop the voltage, what we'll see later is we make a coil here with less turns. We'll call that the secondary coil, NS, that has some terminal voltage Vs, the secondary voltage, and a current Is, the secondary current. What happens when we put power into our primary coil? By induction, we'll create a current in this circuit, but the voltage will be less than this one based on the ratio of the number of turns in the coils. So for an ideal transformer, right here we're trying to drop the voltage from this one to this one, and then power something stupid over here in this rectangle. Okay, so this is the basic idea of our ideal transformer setup. What we're going to do is work out how exactly this works and why we come to those conclusions. So basically, it's a combination of the two types of inductance we talked about earlier. Look up here at the top. The induced EMF in the primary coil is going to be based on the self-inductance of it on itself and the mutual inductance of it due to the other coil. In the secondary coil, we will have a contribution of it on itself and it due to the other coil. So this is the general picture here. As you can imagine, it can be very complicated. We're going to simplify things based on the ideal transformer setup, but basically this package here is what you would use for more complicated scenarios. We're going to simplify it by saying for an ideal transformer, the flux is perfectly preserved in the two coils, so d phi dt is the same for both. We can write both in terms of the number of turns and flux like we did earlier in the lecture. So we have these two expressions here in terms of d phi dt. Those are the same. We can set those two equal to each other, and what we're left with is a ratio between the epsilons and the n's. In other words, the EMF in the primary divided by the EMF in the secondary is always equal to the number of turns in the primary over the number of turns in the secondary. So the consequence is, if we have more turns here and less turns here, we will drop the voltage in the secondary circuit. We'll talk about this more on the next slide here, I believe. We have this ratio here, and in the case of this idealized setup in the steady state, the induced EMF is the same as the terminal voltage. So we can get a relationship between our terminal voltages by plugging in epsilon P equals Vp and so forth. If we have a smaller number of turns in the secondary coil, we get a smaller terminal voltage in the secondary coil. So this is the basic rationale for why you can use a transformer to drop voltages from the primary to the secondary circuit. And this is the basic idea behind modern day transformers. Now, in the modern day, they have like cores through the coils, and they're more complicated than we're putting here in the ideal case, but the same basic idea applies. We are dropping the voltage from our primary to our secondary circuit by using this property of induction here. Okay, so we have a ratio relating the voltages to the numbers of turns. What about the currents? The only thing we haven't addressed in this diagram yet is the primary and secondary currents. So how we can introduce this into the scenario is using the facts about power that we discussed. We said for an ideal transformer, all of the power that goes into the first one comes out of the second one. So if the primary power equals the secondary power, is we use the P equals IV equation. We set IV for the primary circuit equal to IV for the secondary circuit. Then we can rearrange and get another ratio for the voltages. So we can combine it all together with our terms, and we have a relationship between the voltages in the two circuits, the number of turns in the two circuits, and the currents in the two circuits. The interesting thing we find is that, well, Vp over S and Np over S are equal. The currents are the inverse. It's Is over Ip is the relationship here. So you can use these relationships to figure out, okay, I have this voltage, I need to drop it to household levels, I need to make a coil with this number of turns, have this amount of current. You can relate it all using these ideal transformer relationships, okay? So as I said, this stuff's very important, especially for those of you going into double E, but also some other branches of engineering, getting into power generation and stuff like that. So have fun looking into it. Wednesday's our last lecture before midterm 2. We'll be talking about power generation, another super cool topic. Yeah.